This is the second section of Chapter 19 on magnetic fields. This is, in a way, a completely different idea. All the principles are the same, okay? Areas, currents, things like that. However, it's all about a little bit more detail and discussion because it's kind of the opposite, in a way. So, I'm going to run through section 4 and 5 together. So 4 is about the idea and the concept. Section 5 is actually getting into the kind of crucial two details, the two laws that make it all work, and is the basis of everything, any question you're going to get on induction. Okay, so if we go on from where we were with this idea of how to measure field strength and so on, we're actually going to move into a slightly different idea, which is magnetic flux. Now, flux is actually to do with, just that little, flux is actually to do with the lines. So we're talking about the flux lines here, and this is far more important for induction because it's actually about trying to cut across these lines. So if you imagine your wires that you had with the forces, those were working best when they were across the wire, across the field lines. Now, if we move across the field lines, then what we get is our charges that are in our piece of wire, for example, if that was a coil, if we move that, then we are actually basically creating a current. Our current is the fact that we are physically taking those electrons and moving them sideways. And as we do that, our left-hand rule again means that we end up putting a force on those electrons and they will start to flow. So actually it's crossing each of the lines that makes a difference. Think of each one of them as producing a force on the charges that flow through the wire. Okay, so we're going to come up with a definition which is magnetic flux. And the reason we still use flux density is because it's a very simple idea if we do this. So we have a symbol which is a capital Phi, okay, and it is the flux density multiplied by the area of the coil, for example, or the area moved through. So it's all to do with the field, but how much area of field do we move across? So flux density and flux are related by the density of the lines through a certain area. So that's why we still use this phrase instead of field strength. You'll see the Weber's unit. Okay, so it's Germans who did a lot of research on this. So this is Weber. Okay, WB, not W, because that is obviously watts. So just be wary of that. Now, we tend to use this rather than actually have to put this in. Okay, so rather than come up with the basics. Now, if you think about what that means, this is fairly obvious. Okay, if we have a coil of a certain area, then if we have that area, then how many field lines go through it? That is our flux. It's that simple. But if I take my coil and I turn it, then as you can see in my video, you're seeing less area through the coil. So the actual data book equation has just the simple idea of using components again, and it always uses cos theta. Okay, so cos theta is for the angle shown. So theta is the angle from the maximum. Okay, cos of 0 is a maximum. It's 1 lot of BA. So that's your 0. As you turn it around and reduce it more and more and more as your coil turns or your field turns relative to it, because it doesn't matter which one you're moving. Okay, it's all about that comparison. We need to use that version. So technical language, it's the normal to the loop, okay, or if you prefer a bit, it's that idea of the axis, so the central axis of the loop. Again, not a definition, but it's just that way of remembering it. So it's all about having something at right angles. Now it kind of goes together with our cover picture, because there is our axis straight down the middle, and strangely enough you can only move things down through a loop, so that's why we tend to measure angles from there. If it came in at a glancing angle, then you're going to reduce the effect. So the idea is coming perfectly, your best shot is coming perfectly perpendicular to the coil. Most of the time we are talking about coils, but not always. Okay, so I'll just put in, to make clear, that is for the angle shown in the diagram. Okay, so it's that angle there. Right, so that is our key crux idea. Okay, now we do occasionally, but pretty rarely, get this idea of flux density and so on. So this idea of what a Tesla is is 1 Weber per meter squared, or per unit squared area. Okay, so again, it's that link just through that equation. Nothing fancy. So that on its own isn't that important. And the reason is that when we're doing anything to do with making electricity, which is what this chapter is all about, we tend to have a coil. So rather than a single loop, we'll have lots of them. So every single part that we manage to make electrons move in will produce a current. If you've got 2 coils, then you're going to actually move twice as many electrons at the same moment. So you're going to have twice as much current. So we have a far more useful context and phrase that we use, which is called not the flux, but the flux linkage. Okay, now flux linkage is really important. Okay, so flux linkage is simply n phi. Okay, but it's that phrase. So don't talk about flux, talk about flux linking to the coil. So how much of the flux is being, shall we say, picked up by the coil. So if you have your coil and you've got a lot of flux through it, well, several turns on that coil will pick up more of the flux. And the whole of this topic is about how to trap as much energy from the field. So flux linkage is the phrase to use. Okay, just keep sticking with that. Now we've mixed it up with what we just got. We get a kind of more user-friendly area. So this is the B times A is that one, multiplied by N. You'll see that pick up quite a lot. So notice the similarity with where we had the magnetic field strength, flux density through different coils. Okay, so similar kind of setup. So that is our basis. That's the thing that we're going to use. N is just a number of turns, or N loops if you prefer, and so the unit is still Webers. Okay, it's just a larger Webers. So let's just pick up on that. Apart from obscure examples, which we can have a look at, we're going to really talk about coils and things. Now, officially, if we go to the data book, they don't actually go much beyond that. He says, looking for his data book, here we go. If you look on the very back page, okay, under electromagnetism, just be careful. Magnetic fields are there. Electromagnetism is actually just this second part of just creating electricity, inducing a current. So we've got our equation in there, okay, as put on my notes that. We have this one, there's nothing else in between, okay, and then there's this bit down here, which is a bit like one you did at GCSE, which we'll pick up on. So most of the time they are not going to go into any detail. Some specs go into loads of detail, but we don't on here. But we are going to pick up on this crucial idea of flux linkage and that second equation, which is how quickly that changes. So let's take an example here. Okay, we have, again, it's probably beyond the course, fingers crossed you say, but if we take a coil that's rotating in a field, okay, so here's our end view, okay, ignore the plus and the cross and the dot as such. It's to do with the idea to just show there the ends of the wires. So we have a loop that is perpendicular to the field, okay, it's that direction, and it's spinning, and our flux spins round as it does it. Example. in picture 1, if I take my coil, if you were the field, you would see that. Picture 2 is where it has rotated and you cannot see through the loop at all. Picture 3 and then picture 4. So in one complete turn we're actually getting 2 views, or 2 maximum views through the coil, and then it reduces to nothing. Okay, so that's what that picture represents there. Now all we have to do is go back to that equation up at the top. So to start with, our flux linkage, okay, sorry, I don't know where the end's gone, written like that, okay, our flux linkage is going to equal BA, and assuming it's got n turns, then it's going to have n. But in the version here, if we measure this angle, well, if we take the, again, central axis of our coil, then what we've got here is a 90 degrees, here we've got 0 degrees. What we'll find is we can still use that same equation from before. Okay, so flux BA cos theta just scaled up by number of turns. Okay, so that can use, depending on how you look at stuff, it can be used in a really useful way, because most generators tend to be a spinning coil. Okay, so the mathematics actually is really useful to think of it like that. And if we were to think of how quickly it's turning, then basically that creates our electricity and how large the amount of current is that flows. If any of you have ever seen a bike with a dynamo, a push bike, bicycle, they're great. They're really bright because they can produce a lot of electricity, much more than LED lights in a way. But as soon as you stop turning, you'll stop changing the amount of flux through your coil. Everything just turns off. But it also means, and you may have noticed, that if you drive faster in some cars, cheaper cars without regulators, or on a push bike, what you'll find is the light gets brighter. So the speed at which you do this releases more current. Using logic, if you've got more kinetic energy, you're going to create more electrical energy. Okay, so we can use that kind of principle to work us through. Now, we could step that up as well, because we could think about the rate of which it turns in terms of omega as well. So again, we can use our maths of what we've done before to just kind of keep adding on to our equations. So our flux linkage is just going to be BAN, in this case, cos omega t. Okay, similarities with SHM are obviously there as well. Okay, so you know, we can still do all the same mathematics, but base it on that idea of flux linkage. So there's a lot of things to play with. Now it's worth pointing out just little details here. I'm going to rattle through because you can pause the video and have a look at it. But what we're getting is, that means, again, because it's a sinusoidal graph, if you were to plot that, what you'll find is at some moments you've got maximum flux flowing through, some moments minimum, but if we want to think about moving our electrons, then we need to move them across our wire. So actually here, although flux is going through the coil is very small, the flux linking the coil is small, 0 in fact, this wire here is cutting through as maximum number of lines per second. It's going through a lot of lines every second, a lot of flux every second. Whereas here, this kind of is just sliding between the lines. It's not really cutting any field lines. So when we're looking at the next step, when we look at what this does, it's a little bit counterintuitive. Okay, if you're capturing a lot of flux, then that flux is not really going to change much. If you're not catching much flux, actually that's when you create the most force on the electrons. So that's when you're going to get the most current. Okay, so these are our maximum points, these are our minimum. If you compare this to a motor, it's exactly the same principle. Yeah. So when the motor coil was flat, that's when you got your biggest turning effect, your biggest force from the current you put in. Here, if we're turning through that flat point as well, you'll get the maximum current out of it. So you'll get the same angle will produce the same effect, but in reverse. Biggest current out, electricity being generated or induced, and in a motor, biggest force out, biggest turning effect. So, useful little link maybe. Okay, but this is the crucial little bit, is trying to visualize that. So have a good think through this. If you have a bit of a wire or something, try and, or maybe a flat disc, maybe a saucer, just try thinking about how that looks and visualize that in your head. That'd be really useful. Okay, the second bit, or part 5, is moving away from the kind of basic theory and actually gets us into the black and white stuff of what actually is electromagnetic induction. So, when we're talking about EMF, the phrase EMF has come from this originally. So it's the work of Sir Michael Faraday and others who realised the force due to the magnets on the electricity all linked together. Okay, so this is where it all started to happen as such. Now, we can create voltage in a coil, we can generate electricity by creating voltage, and we can also create current, because obviously when you have a voltage you have current. But, and this is the crucial bit, only one of these is truly correct. Okay, only one of these is always true. And that's where Faraday's law comes in. Okay, so we are going to induce an EMF. So the phrase induce means it's already there, but nothing's happening. We're going to induce movement. We're going to create the electricity because we might make the electrons move along the wire, and therefore you have current. Okay, so that's our kind of crucial little bit. So hence the induction. Lenz's law is the awkward bit, and we'll come back to that in a second. We'll build that up ever so slowly. It's a little bit counterintuitive, but actually it's fundamental to physics. So, making electricity. Here's our crucial bit. You've done a little bit, or you should have done a little bit of this in GCSE. You don't need to go beyond that. Basically, how do you make electricity? Well, there's several ways, and the most obvious is to move the magnet around, okay, relative to the wire. But the crucial bit is it has to go across the wire. Okay, Faraday's left-hand rule again. Okay, so it has to move at 90 degrees to it. Now, there is a brilliant animation. Guess what? I'll put it in here. So I will say right at the beginning, look at electromagnetic lab on, guess where? PhET. It is one of their best animations. It's really good. You start to really get a big idea what's going on. Okay, they've got a little paddle wheel effect. However, they've also got a coil and a magnet you can move around. So experiment. Try moving the magnet along the field lines. Okay, so slide your magnet along the wire, no effect. Cross it at a bit of an angle, you'll get a little bit of an effect. Cross it at 90 degrees, you'll get most effect. Okay, so it's all about moving the magnet across the wire. Now, we could, of course, if you think about it, move the wire across the field lines, which is just the same thing but viewed from the other angle. So if you are the wire, are you moving or is it the magnet that's moving? Both of them, the phrase that's really useful to use, both for visualization and in terms of putting in your answer, which is fine, so you can put it in descriptions, they are cutting the field lines. So if this was your cold hand, if this was your magnet, okay, my hand was the magnet and the field lines coming out the end, if you move your wire that way, okay, or move it that way, nothing's going to happen. But if we move it across like that, across like that, or of course move that, we're going to have the same effect. So those will create, because you're cutting through each of those field lines. All the field lines are cutting through your conductor, so it doesn't really matter which. But there is also one other effect, and this is really important, for example in petrol cars. Okay, what you need to do to get the spark for the engine is actually not move anything, but you just need to change the field. Okay, so change the flux traveling, because if the flux density changes, we're moving lines of field of flux closer together, further apart. Well, we're going to change effectively by keeping it still. We're going to change how much goes through. A bit more obvious with a coil. So if I get my coil, yeah, if I did this, I'd only have 3 of my fingers going through. But if I shrink it down, I could get all of my fingers through. So just changing the strength of that magnetic field will actually create a change in here. Okay, so those two are obvious, but that one is an important one. Have a think about that. Okay, and I filmed a little video where basically I've got effectively a simple transformer, and all I'm doing is turning it on and off. You learned at GCSE you need AC current, alternating current. You don't. You actually just need to change the flux density, change the strength of your magnetic field. Okay, that will have the same effect. So, a little bit down here about cutting, because that's probably the most visual way of doing it, and then we'll come up with the 2 crucial things. So, effectively, I've already told you this, because this is what's going on here. Okay, so Faraday's law is a really nice, I think obvious way of looking at it, but it is unfortunately one of these that is a law. Okay, so again, you do need to learn that. Okay, so the magnitude of the EMF, notice that EMF, so the magnitude of the voltage, if you prefer, induced in a conductor equals the rate of change of flux linkage. Okay. I don't think there should be an S there. Just flux linkage, not flux linkages. That doesn't make sense. So that bit there is really crucial. It's all about the rate of energy transfer, which if you think about it is power. So that does kind of link in together. So the symbol for EMF that we learned from last year is that epsilon. So it's voltage you're creating, it's not current. We'll come back to why in a second. And that is the, I know I said rate here, but generally it's written down as n phi. So there's your flux linkage per second. Okay, and again, in your data book, it's actually written down as delta as well. So more usefully, we can think of, rather than any moment, although that is technically more correct, we can think of it in the bigger picture. So if, for example, our coil here, we could simply find out how much flux was going through at that stage. A quarter of a cycle later, let's say this is rotating once a second, then a quarter of a second later you've gone from BAN for your flux linkage down to 0. So all you'd have is your change will give you BAN minus 0 divided by a quarter of a second. Okay, and that gives you the hint that the faster you rotate your coil, the smaller your time will be between each quarter turn, and so your average EMF, I should point out that's not instantaneous, but for average for that quarter turn will be just simply BAN divided by the time. And so you'll get a larger and larger and larger voltage the smaller and smaller and smaller time you can see this. Now what that does mean is you can create some huge voltages from a simple circuit that has, I don't know, maybe a 10 volt battery, or in a car a 12 volt battery, for example, by turning this flux linkage, turning the field on and off in a really short time. So you can create thousands of volts, which is enough to spark your spark plugs, from a 12 volt battery by going through the coil, as it's called on the car, and by turning it off quick enough. Okay, by doing that through the distributor, the switch, as it flicks on and off, you'll see that you can create huge sparks. The logic is there. But a more obvious example is in your phone. If you've got a flash in your phone, flash gun for your camera, well, that needs several hundred volts, and you don't have a several hundred volt battery. It would melt your phone if you tried using high voltages. So it's a small voltage, so it creates a small magnetic field in a coil, in a choke it's sometimes called, and then you just turn it off very quickly, and that produces again a really high voltage. Okay, so really powerful idea, that equation, really powerful. I should say there's one bit missing out of that for the equation, but that is Faraday's law. The bit missing is Lenz's law. So we'll come back to that one in a second. Okay, so here's one of the slightly more obscure ones, because most people tend to think about coils, but they don't always think about the other bit. Imagine a wire shooting across a magnetic field. Okay, just like we had a wire in a magnetic field being pushed sideways. This could be an aeroplane with a certain wingspan flying through the Earth's magnetic field. And you get it with your car driving along the road. You will actually induce a voltage across it, assuming your car or aircraft or whatever it got is metal, or conducting rather. You'll create a voltage between the two sides due to the rate at which you drive along the road, because you're going through a magnetic field. Now, nearer the equator, the field is parallel to the surface. You're not necessarily going to cross the lines, the flux lines, field lines. But nearer the poles, this gets more and more problematic. And I can say, North Canada, for example, you can produce some quite big voltages. But planes obviously travel a lot faster, and so they're cutting through much more field lines. And again, a lot of the transatlantic flights will go the shortest way, which is actually over near the North Pole, over Baffin Island, places like that. So let's break that down. Can we use that? Well, yes, we can. It's actually a lot simpler than it looks. Okay, so we'll start off with the key idea that Faraday's law, so I'll just repeat it, the flux linkage, rate of change of flux linkage. I'll just keep saying that. The EMF is the rate of change of flux linkage. So if we want to think of one piece of wire, well, we can simplify it a little bit because we don't have N turns. So effectively, just to simplify it a tiny bit, delta phi by delta t. Now that's important because most people will then kind of go, I can see what I'm doing now. Okay, so what was, how much flux is there that it cuts through in the time it gets from here to here? It'd be times A. Okay, so how much area has it swept through to get to the other end? So as B is constant, I've got a giant box, I'm not sure why, you don't need this much box. What we end up with is change in BA over delta T, that's, excuse me, terrible way, which equals B times delta A over delta T. Okay, so it's a constant flux density, therefore it's the area swept out per second. If you're travelling at a certain speed, well, the area per second is going to be length times by that distance. Okay, and S equals UT, oh sorry, VT, I've got there, so VT. Okay, so what I need is S area is, delta area, looks like delta, delta area equals L times by S equals L. I'll make my L's look a bit different, so there we go. L times VT. Okay, and of course, if I want to think about the fact that it's not the area but the area per second, then we just end up with epsilon equals B LVT divided by T equals BLV. Okay, and I'll just put again EMF on the end. So it's not hard. It's always starting with that and just thinking, can I bring the area into it? Because if you can, BAN, for example, or in this case AN, then BA, then you'll find it actually breaks down into simpler stuff. So again, equations not on the data sheet. It can be something they're asked to do, but you'll spot this because it's a moving straight line thing through a field. Okay. If the field is not perpendicular, if say you're at the latitude of Earth of the UK, the field lines are curving downwards, so there's a dip in our magnetic field. It's not vertically downwards like it would be at the North or South Pole. At the equator it's there, so it's somewhere in between, where you just add in your cos theta or multiply by cos theta. So it doesn't get any harder. You just need to keep simply thinking about the same stuff. Now, as I mentioned there, okay, the best way of doing this, so I'm going to give this a little bit of a health warning slightly, is your best way is think of the average EMF, epsilon, is the amount of, let's just change BAN, okay, assuming you've got N coils again, divided by time for a quarter turn. Okay, so keep it simple because that's going from maximum to zero or zero to maximum flux linkage. Okay, so that's the easiest one. However, instantaneous is a little bit more tricky, but again, I think this is probably going beyond our course, but any instant in time, you just need to break it down a little bit more, and you just go for, of course, that same idea, okay, BAN, but what we end up with is cos in there as well, because it all depends on the angle that it's turned through from the central axis compared to the magnetic flux lines, and it turns into a dt and dBAN cos theta because it's at an instant. And if you put that in, well, omega t, and you can bring the whole lot in, you end up with, if you want to do the derivation of it, then you'll be able to see that all those constants are still there, and that turns into sine omega t. Okay, but that is, as I say, very much in the background there. But again, it is, sorry, I've missed one out. I'll put it in the beginnings. It brings us in that idea of omega. Okay, so it's very similar, but that actually is the kind of more usual way of doing it, because you usually have a spinning coil. But at any moment in time, yeah, we should differentiate to get the key thing, and that shows us that voltage changes with the rate of change of flux linkage. Okay, flux linkage is there, rate of change. And at any instant, it looks like a sinusoidal wave. Guess where this comes from? All that AC wave stuff. I'm just going to jump ahead a little bit. That's why you learnt all of this at GCSE. Okay, all of these things about AC currents, or alternating currents. Okay, so they're little asides. Okay, that's the crux of it up there. If we just move on a little bit more, we need to cover the other law, and this is the descriptive stuff, and this is where it gets a little bit awkward, and it's all about the direction. So it's not about the size of it, it's the direction, and it all leads into just effectively that negative symbol being added. Okay, what does that mean? Well, mathematically you can figure out that the EMF must be in opposition. So for example, you know, that if it's going up on a graph, so let's just go to AC kind of idea. If we had that as our flux linkage, where it's going up, our voltage is actually going down. Okay, becoming negative. Still increasing actually, but it's going in the opposite direction. What is that about? Well, the idea is actually quite simple. It's conservation of energy. So if you try and force electrons to move, they are going to try and stop you. They don't want to move. Okay. Now it brings us into a whole load of interesting things, and I've done a load of little video clips for you to watch already. But the idea is simply, if I was to take a magnet, let's say this, let's move out there. If I was to have a magnet here, then what it will do is, as if I keep this like this, nothing happens. But as soon as I move it, I'm going to create a force on the electrons. These are all going to move in here, according to Faraday's left-hand rule. Okay, so keep with that. So the direction of the electrons move, assuming it's a complete coil, will create a current. What if it's not a complete coil? What if it, like this, actually has two connections? So a wire there and a wire there. The two ends of the wires are not connected. Okay. If I do not connect them, so I do not have a complete coil, so it goes round and round, but I have two ends sticking out, then I will still always induce an EMF, but no current flows. Okay, so when we talked about induced current, when you hear about that, you have to have a complete circuit, because if you don't have a complete circuit, you don't have current. We know that. Okay, so let's just pick up on the key little bit here, is that if I try to, if I do have a complete current then, I'll put that in. If I create a magnetic field, the magnetic field made in here tries to stop this moving into it. Okay, the little electrons are going, no, 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 and they try and push you away. So what I get is the magnetic field here creates a north pole here, if this is a north pole. So as I try and push it in, they will try and repel it. That's Lenz's law. It also works in reverse, in that if I try and pull that away, my magnetic field again tries to stop it. So north pole, this will become a south pole and try and stop me pulling away. So as I push it towards it, it will create a current in one direction. As I pull it away, the direction of the current swaps. Okay, and it's always trying to stop me changing my movement here. Okay, so if I push that in, it's going to stop me. If I pull it out, try to stop me. And it's always to do with the induced current. Now, crucial step back, and this is why the voltage current thing is important. At the moment, without these connected, nothing's going to happen. I will create a voltage, my electrons will move, but a bit like a capacitor, they'll only move until they can't move any further, which is not very far. So no current will flow in the coil, so no field is produced by the coil, back to our first lesson on magnetism, and so nothing happens. Okay, I can just move that in and out, no problem at all. But if I connect these with a wire, so I've got a complete loop, complete circuit, it's suddenly much harder to move things in and out. And there's a great little video I made, which effectively you would normally do as a play around demonstration, but you'd play around with it, is a copper pipe. So it's a good conducting pipe, it's not magnetic, so that's crucial, otherwise your magnets just stick to it. Drop a magnet down a conducting non-ferrous pipe, and what you'll find is the voltage creates a current that flows around the pipe, and that current creates a giant magnet and it stops it going down. So you drop something through that's not magnetic, goes through fairly quickly, just using SUVAT. If you drop a magnet through, it goes down really slowly because it's always being opposed. Now, if we do this as an experiment and drop it through, or like with my original picture, what happens is we can measure the voltage being created. So we can have a CRO, an oscilloscope, and that will pick up that voltage, and then they'll get a positive spike as it goes in, and then as it drops out, so our south pole is, so at the moment it is dropping in, I get a north and a south from my current here, but if it goes down below it, then what will happen is the south pole is trying to be attracted by a north, so this swaps over, my voltage swaps over, and I get a different effect. Okay, so repelling, and then it's in the middle, it's stuck in the middle. Okay, as it's going through the middle, you're not cutting through field lines, flux lines, so there's no voltage. And then as it tries to come out the end, again, because our magnetic field's spreading from the ends of this, you'll get the coil in here trying to attract it back. Obviously it doesn't work because gravity is stronger overall, but yeah, it tries to attract it back. So you get a positive and a negative voltage. And it's very, very symmetrical, except one of them is moving faster. So if you drop it through, it's actually, of course, moving faster underneath because gravity is making it accelerate, or the force due to gravity is. So you'll find that the time here is shorter. Okay, the second spike is narrower, but taller, because the rate of change of flux, okay, flux change per second. If it's going faster, there's less seconds, but it's still the flux change. So the area underneath each half will be the same. However, let's just do a sketch. So that area will equal that area, but this will be, let's say, much narrower and taller. Okay, so same amount of flux change, but different rate as it builds up speed. Okay, so really, really common, complex idea, but it's this. The hard bit is, to be honest, trying to explain Lenz's law. And the easiest way of doing it is being a little bit vague. Okay, so direction of EMF induced. If you want, you could say current, question mark. Okay, but EMF will always be correct. In a wire, in a loop, in a whatever you want, coil, is such that it opposes the change. Okay, it's a lot quicker than trying to say it creates a magnetic field, and the magnetic field opposes the original magnetic field, and so, you know, So you just go down the opposes the change, but yeah, the fields are trying to repel again. Okay, now this is, to round it all up together, where people get into this horrible idea with, oh, is it a left hand, is it a right hand, etc. Faraday's rule. Okay, the fact that these are in opposite directions is Lenz's law. So don't do that. Stick with the left hand rule. Okay, Fleming's left hand rule, and just think the opposite will happen if you're creating electricity. Okay, so we've still got all of that stuff with the right hand grip rule. Okay, that still works. But as I've said on the next page, if you try and push a magnet in or try and pull it away, it will always try and stop you. So as my physics tutor told me, it's the only thing I remember is from his lessons, apart from his strange ties, was if you push this in, this will have a repelling face. So it's basically saying, no, 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 no. You try and push your magnet in, it's going, no, 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 fighting you off. If you try and pull it away, it's going, no, 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 and trying to stop you taking it away. Okay, so it's trying to always stop you do what you are doing. Okay, and that's why I've underlined the word could in the text. Okay, I would avoid it. I would just stick with that currents that flows will always be in the opposite direction. Okay, and that's far easier to stop you getting mucked up in your mind with, is it the left hand or the right hand? Right hand grip, left-hand Fleming's. Okay, so I'm going to stop there. The rest kind of jumps sideways from that. That is the crux of the idea, particularly these two laws, Faraday's and just applying it in different ways. So the size of the EMF, and Fleming's, the direction of the EMF. Let's just put in direction there. Okay, so again, that learn. Okay, so that I would say is, I would learn that by word by word. Okay, and I would stick with EMF, it's probably better. So learn that by rote, memorize it, that will always be right. Okay. So, okay, we will go into the applications of it. We'll jump onto this, which is using this. You do need to know your way around it. Obviously, you would have done a lot of practicals with it by now. Hopefully, we'll get back fairly soon and do ones with capacitors and stuff, and we'll also do a little bit in induction. We're going to link into AC and DC voltages. Again, it's a background idea, but it's really nice because it introduces us back to RMS, root mean squared values. Okay. And then the last bit is nice and simple as such, in that it's about transformers, but beautifully it explains or links together all of the ideas that we've had. So creation of magnetic fields, induction of currents, etc. Okay, and induction of voltages. So we will go into this one with a little bit more depth. I'll probably do that all in one thing. So this, I suspect, will be reading week over February half term, just going through. I've recorded some videos for waves for the lower six, so you can go and have a look at that. How does the two controls work, things like that. Okay, but other than that, we'll leave that there. Big chunk, but a really important one. Basically, the whole of the other half of the chapter.